So in this video we are going to discuss about crystal field theory. That is, who proposed the crystal field theory and why the crystal theory was proposed. So before going to discuss all that, first of all we have to discuss the d-orbitals, because this knowledge is the toolkit for opening the box of the crystal field theory, in which so many contents have been embedded. So now coming to the d-orbitals. D-orbitals. Now we know there are 5 types of d-orbitals. The one is dxy, next one is dyz, next one is dxz, next is dx square minus y square and dz square. So this is the first d orbital, second d orbital, third d orbital, fourth d orbital and fifth d orbital. So these are the 5 d orbitals. Out of the 5 d orbitals, these 3 d orbitals, dxy, dyz and dxz, are called as T2g d orbitals. T2g d orbitals. And coming to the remaining 4th and 5th one, both are called as EG d orbitals. EG d orbitals. Now what do you mean by T2g d orbitals and EG d orbitals? T stands for triply degenerated d orbitals, whereas E stands for T stands for triply degenerated d orbitals and E stands for doubly degenerated d orbitals. What do you mean by degeneration? That is, the energy associated with these 3, first, second and third, is one and same. That particular concept is called as degeneracy. Then if the energy associated with the orbitals is one and same, those orbitals are considered as degenerate orbitals. Now these are the 3 orbitals which are associated with the same energy. That's the reason this particular class of d orbitals is notated as T2g d orbitals. And the remaining 2, dx square minus y square and dz square. So these are the d orbitals, 2 d orbitals which are associated with the same amount of energy. That's the reason these are called as degenerate orbitals, and since these are 2, these are called as doubly degenerated d orbitals. Now I will throw some light on the structure of each and every d orbital, right? Structure of every d orbital. So do remember that the d orbitals have been classified into 2 types: T2g set of d orbitals and EG set of d orbitals. Now let us try to focus what is the structure of each and every d orbital. First let us talk about T2g d orbitals. So in the T2g d orbital, first we are going to draw the structure of dxy. dxy. So what do you mean by dxy? What is the structure of dxy? So for getting the structure of this particular d orbital, what we need to do is, there is no need to buttify the structure. There is no need to buttify the structure. dxy, right? Now, just a moment. Out of the two, out of the 2, that is dxy, one axis is x-axis, another axis is y-axis. One axis is x-axis, another axis is y-axis. Now in dxy, d orbital, the lobes are placed between these 2 axes. Lobes are placed between these 2 axes. If the lobes are placed in between the 2 axes x and y, then this particular d orbital is called as dxy. This particular d orbital is called as d dxy. Now coming to the second d orbital. What is the second d orbital? dyz. dyz. So coming to the second d orbital, so it's very easy to remember the structure. Out of the two axes, one is y-axis, another one is z-axis. Now if the two lobes are placed in between these y and z-axis, then this particular d orbital is called as dyz d orbital. Now coming to the third one. Third one is dxz. 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 That is, one axis is x, another axis is z. Now if the lobes are placed in between these x and z axis, then that the particular d orbital is called as dxz orbital. dxz orbital. Now what do you mean by this? That is, lobes are placed, when the lobes are placed in between x and y axis, dxy. When the lobes are placed in between y and z, dyz orbital. When the lobes are placed in between x and z axis, then the d orbital is dxz. What do you mean by placing the lobes? Placing the lobes means the electrons concentration is high in between the lobes. That is, the electrons are sitting in between the lobes in the case of dxy, dyz and dxz. That is, electrons are sitting in between the lobes. In the case of dxy, the lobes are placed in between x and y. In the case of dyz, the lobes are placed in between y and z axis. In the case of dxz, the lobes are placed between x and z axis. Now what do you mean by this? That is, the lobes are placed in between the axis means, the electrons are sitting in between the axis in the case of these set of d orbitals. Electrons sitting means what? The concentration of electrons in between the axis. In the case of dxy, dyz and dxz is high in between the axis. And this particular set of d orbitals are T2g d orbitals. T2g d orbitals, already I have discussed that. T stands for triply. As the 3 are there, it is called as triply. And the energy associated with this 3 d orbital is one and same. That is the reason these are called as triply degenerated d orbitals. So to summarize, in the case of the T2g set of d orbitals, the electrons are sitting in between the axes. Electrons are sitting in between the axis means the concentration of the electrons between the axes is more. That is the meaning of this. Now coming to the next set of d orbitals, that is EG d orbitals. What are having? We have 3 are over. So fourth one is dx square minus y square. Now coming to dx square minus y square, one axis is x, another axis y. Now if the lobes are placed along the x-axis and y-axis, then it is called as dx square minus y square. If the lobes are placed, if one lobe is placed along the x-axis and another lobe is placed along the y-axis, then such d orbital is called as dx square minus y square d orbital. Now coming to the last d orbital, that is dz square. In the dz square d orbital, the one lobe will be along the axis. Another lobe will also be along the axis. Now this is the another lobe of this another lobe, back lobe, we can say that. This is the back lobe of a dz square. This is one lobe and this is the back lobe. Now in this case of dx square minus y square dz square, the lobes are sitting along the axis. Before that, what are these two orbitals, d-orbitals called? These two d-orbitals are called as Eg d-orbitals. Eg d-orbitals. What do you mean by E? E means doubly degenerated. Since the d-orbitals are 2 and the energy associated with these two d-orbitals is 1 and same, these are called as doubly degenerated d-orbitals. Doubly degenerated d-orbitals. In these doubly degenerated d-orbitals, what is happening? The lobes are placed along the axis. The lobes are placed along the axis means what? That is, electrons are sitting along the axis. That is, the concentration of electrons along the axis is high. So in this case of dx square minus y square, the lobes are placed along the x and y axis. That is, the electrons are sitting along the x and y axis. That is, the concentration of electrons is high along the x and y axis. Coming to dz square, the two lobes are sitting along the z axis. That is, what does mean along the z axis means? The electrons are sitting along the z axis. Along the z axis, that is, the concentration of electrons along the z axis is more. Right? So this is about Eg d-orbitals. Right? To summarize about the Eg set of d-orbitals, in the Eg set of d-orbitals, the electrons are placed along the axis. That is, the lobes are placed along the axis means the lobes are placed along the axis means the electrons are sitting along the axis. That is, the concentration of the electrons along the axis is more. That is right. So let us try to recapitulate. In the case of T2G set of d orbitals, the lobes are placed in between the axis, means the electrons are sitting in between the axis. That is, the concentration of the electrons is high in between the axis. Whereas in the case of Eg set of d orbitals, electrons are sitting along the axis. That is, the concentration of electrons is high along the axis. So with this information about the d orbitals, let us discuss about crystal field theory. Crystal field theory. First, let us see who proposed this particular theory. This crystal field theory was proposed by the two scientists, that is Brett and Van Vliet. Brett and Van Vliet. These are the two scientists who proposed this crystal field theory. And this crystal field theory clearly explains about ionic crystals. Clearly explains about ionic crystals. Since this particular theory clearly explains about ionic crystals, this particular theory is called as crystal field theory. Crystal field theory. Right? So, crystal field theory was proposed by two scientists, Brett and Van Vliet, and it is applicable to explain the ionic crystals. That is the reason this particular crystal field theory is called, that is, it is called, the theory is called as crystal field theory. Now let us see the salient features of crystal field theory. Salient features of crystal field theory. CFT means crystal field theory. The first salient feature is a complex is a combination of the metal. A complex is a combination of a metal surrounded by the ligands. Complex is a combination of the metals surrounded by the ligands. Now, what do you mean by ligands? What do you mean by ligands? Ligand can be either the atom or the molecule or the ion which can donate its electrons to the metal. Which can donate its electrons to the metal. Now these ligands can be either negative or neutral because the metal ion is positive. So this is how the complex is going to result. The complex is a combination of the metals surrounded by ligands. Now what is the nature of the metal ion? Nature of the metal ion is positive, electropositive. Since the nature of the metal ion is electropositive, so whatever the ligands which are attached to this electropositive metal ion will be definitely either negative or neutral. Because the combination is only possible if one is positive and another one is negative. Now the metal is electropositive. Since it is electropositive, the substances, the atoms to which it is attached must be either negative or neutral. Negative means what? Excess amount of electrons are present on the ligand. Neutral means what? Non-bonding pair of electrons are present in the ligand. Right? So this is the first postulate, first salient feature of CFT. That is, what is that? Complex is a combination of metal ions surrounded by the ligands. Now as the metal ion is electropositive, the ligand can be either negative or neutral but not positive. Because positive-positive interaction is not possible. Positive-positive combination is not possible. That's the reason ligand can be either negative or neutral. Now what is a ligand? Ligand is either the atom or molecule or ion, whatever it is, but definitely it should carry the negative charge or neutral. So now coming to the second salient feature of CFT. The second salient feature of CFT is if the ligand, so only two possibilities are there for the ligand. It can be negative or it can be neutral. It cannot be positive because it is interacting, it is combining with the electropositive metal. Since the metal is positive, definitely the ligand is either negative or neutral. So if the ligand is negative, then the ligand is called as point charge. The ligand is called as point charge. On the other hand, if the ligand is neutral, then the ligand is called as dipole. The ligand is called as dipole. If the ligand is negative, point charge. If the ligand is neutral, dipole. So example of the point charges. Examples of the point charges are F minus, Cl minus, Cn minus, thiocyanide, etc. Example of the dipole, neutral. That is NH3, ammonia. Ammonia on the nitrogen, one non-bonding pair of electrons is present. Non-bonding pair of electrons means what? The electrons which are not participating in the bonding. It is free to donate the electrons to the metal. Now, other example is H2O. Other example for the point charge. In H2O, oxygen is there, and oxygen contains two non-bonding pair of electrons. These two non-bonding pair of electrons will go in the direction of the ion. So this is the salient feature of second salient feature of CFT. That is, if the ligand is negative, the ligand which is attached to the metal ion is negative, then the ligand is called as point charge. Example F minus, Cl minus, SCN minus, and so on. Negative means excess amount of electrons are at part of it. On the other hand, the ligand can be neutral. Neutral means what? It contains a non-bonding pair of electrons which will move in the direction of metal ion in order to form the complex with the metal. Now, third salient feature which is very important is, this very important point. That is, during the formation of the complex between the metal and the ligand, there won't be any overlapping or combination. There won't be any overlapping of atomic orbitals of metal with atomic orbitals of ligand. There is no overlap. That is, there is no combination of atomic orbitals of the metal and the atomic orbitals of the ligand. Just the bond between the metal and ligand is purely electrostatic in nature. Purely electrostatic in nature. When the metal is combining with the ligand or ligand is combining with the metal in the complex, then the overlapping between the atomic orbitals of the metal and atomic orbitals of the ligand is not possible. Instead, electrostatic interaction will be there between the positively charged metal ion and the ligand. So this is the third postulate. So fourth postulate is the bond between the metal and ligand is purely electrostatic in nature. Purely electrostatic in nature. The bond between metal and ligand is purely electrostatic in nature. Electrostatic in nature. That is, the bond between metal and ligand is electrostatic in nature. Electrostatic in nature. That is, the interaction between positive and negative. That is the meaning of this electrostatic. This is the fourth postulate. Coming to the fifth postulate. So we are saying that a complex is a combination of the metals surrounded by the ligands. Now, whenever the metal is not surrounded by the ligand, it will be in the ionic gaseous form. Ionic gaseous form. Ionic gaseous form. Whenever the metal is in the ionic gaseous form, already we know that there are 5 d orbitals which are possible for the metal. The metal contains 5 d orbitals. Whenever the metal is in the gaseous form, all the 5 d orbitals, 1, 2, 3, 4, 5. 5 d orbitals we have discussed. The first one is dxy, the second one is dyz, third one is dxz, and fourth one is dx square minus y square, and last one is dx. Whenever the metal is not surrounded by the ligand, it will be in the ionic gaseous state, and whenever it is in the ionic gaseous state, then the 5 d orbitals of the metal will be in the degeneracy. That is, the energy associated with all the 5 d orbitals of the metal is one and same. But when metal, that is, when the ligand is approaching the metal, that is, whenever the ligands are added to the metal, what happens is the degeneracy of these 5 d orbitals is removed, by which the energy of these 5 d orbitals is increased. Energy of these 5 d orbitals is increased. That is, they occupy average energy level 1, 2, 3, 4, and 5. Average energy level, which is dxy, dyz, dxz, dx square minus y square, and dx square. This is average energy level. So once again, whenever the metal is not in the complex. That is, the metal is not in the complex means whenever the ligands are not attached to the metal. Now, whatever the 5 d orbitals which are a part of the metal are degenerate. The energy associated with all the 5 d orbitals is 1 and same. But when the ligands are added to the metal for the formation of the complex, then the degeneracy of these 5 d orbitals is removed, by which they occupy the average energy level. So further splitting of these 5 d orbitals from average energy level depends upon the approach of the ligand to the metal ion. Depends upon the approach of the ligand to the metal ion, means approach of the ligand in the direction of. If the ligands are approaching in between the axis, then what happens? If the ligands are approaching along the axis, then what happens? So that we are going to discuss by means of crystal field theory in octahedral complexes, tetrahedral complexes, and square plane.